For years, SaaS data sat behind static, grid-based dashboards. Today, applications rely on interactive visual networks, where users drag, connect, and configure logic physically. This interface style is now a requirement for AI agent pipelines, CRM journeys, and DevOps automation systems, where users most manipulate data directly on a canvas. But engineering these interactions from scratch demands months of development time. Teams often spend their resources solving interface mechanics rather than building the actual product logic. The difficulty lies in the canvas physics. Developers have to calculate custom drag-and-drop coordinates, manage smooth panning across large viewports, and program edges that dynamically reroute themselves when elements move. Because it handles these coordinate calculations and routing updates out of the box, the React Flow library has become the foundational engine used to solve these specific engineering bottlenecks. Look at a production-grade database schema visualizer. The user sees polished forms, specific typography, and clear business logic. If we strip away the UI polish, we can see the raw structural architecture supporting the interface. Peeling back one more layer, the entire system simplifies into a mathematical directed graph, distinct entities, and the directional pathways connecting them. The primary technical tension here is taking that abstract graph data and translating it into interactive React components without crashing the browser's main thread. Mastering this scale requires decoupling the visual components the user sees from the complex state management physics calculating in the background. The architecture relies on three basic primitives, starting with the node. Positioned on a blank canvas, the node represents a single step or task. Users often assume these nodes are static shapes drawn onto an HTML5 canvas. In reality, each node is a fully customizable React component. The engine treats it exactly like any other element in a web application. This allows developers to embed live API calls, input forms, and interactive charts directly inside the node using standard HTML and CSS. The second critical primitive is the handle. These are the explicit connection points placed along the node's perimeter. Handles strictly dictate the connection logic. They specify where an edge is permitted to attach and define the direction of data flow by acting as either a source or a target. Defining nodes as standard components while enforcing strict handle logic allows for diverse UI designs while maintaining predictable data flow boundaries. When we zoom out to multiple nodes, we introduce the third primitive, the edge. Edges define the relationships and data pathways passing between the isolated nodes. Because the user can drag nodes across the canvas, the edges must mathematically recalculate their routing and redraw themselves instantly to maintain the connection. Developers can dictate the specific visual routing of these pathways, choosing between direct straight lines, structured angular steps, or smooth Bezier curves. Here we hit a limitation. The core engine handles the rendering of these elements, but it is completely agnostic to graph topology. It does not know how the data should be organized. To organize this chaos, the system requires the integration of a third-party layout engine algorithm. This algorithm ingests the raw data structure and calculates the optimal positioning for every node to prevent edge overlaps and establish a clear visual structure. While the library renders the connections, external mathematical layout is required to make complex data structures visually comprehensible. Once the layout is established, the application faces its primary failure point, state management. Every single pixel of movement during a drag-and-drop action forces a state update in the graph's data structure. If the state mapping is inefficient, moving one node forces a global re-render of the DOM. All 50 nodes recalculate simultaneously, and the frame rate counter plummets. Think of a smartphone lock screen. Swiping to unlock doesn't force the device to restart its entire operating system. It only moves the visual overlay. Re-rendering a full graph for one node's movement is fundamentally flawed architecture. To solve this, the engine uses a specialized state library called ZooStand to implement an uncontrolled state architecture. This bypasses standard React context bottlenecks by isolating the rendering cycle to only the active component being manipulated. Strict state isolation is the only way to maintain a smooth experience when processing high-frequency user input across the canvas. Even with optimized state, scaling a graph up to 1,000 nodes introduces a new bottleneck. Rendering thousands of complex React components, forms, and charts simultaneously will eventually crush the browser's memory limits. The final architectural solution is viewport virtualization. The engine continuously calculates the canvas boundaries relative to the specific dimensions of the user screen. Using those coordinates, the system explicitly unmounts and deletes any node or edge outside the active field of view from the DOM. This guarantees that memory usage and rendering calculations remain flat, regardless of how large the total graph grows. Virtualization removes the ceiling on scalability, allowing enterprise platforms to map massive data structures without performance degradation. With these constraints solved, we can return to the bare wireframe primitives established earlier. We now reapply the high-fidelity UI elements, the styling, and the business logic over the structural foundation. Beneath this interface, multiple engines work invisibly in tandem. Isolated state handles the physics of user interaction, while viewport virtualization handles the massive scale of the data. Understanding these layers allows engineers to build robust visualization tools without battling raw canvas math. Modern SaaS platforms now rely on visual node editors to make complex data actionable. When users manage automated workflows or cloud infrastructure, traditional text forms fail because the underlying relationships are nonlinear. This architecture shifts the cognitive burden away from the user. The software handles the complex logic tracking, while the user manipulates the spatial structure. The ultimate goal of the visual node engine is to transform back-end data into an intuitive architecture that users can physically control.